Hello students, welcome to EPG Pathshala. I am Dr. Aranya Bhattacharjee from the School of Physical Sciences, Jawaharlal Nehru University, New Delhi. Today we are going to discuss about a module, Heat Capacity of Solids 2, under paper Solid State Physics. So students, let us see what you are going to learn in this module. So what you will learn is about modifications from the Einstein's to the Debye model in terms of the normal modes of vibration. Know about the phonon density of states, constant frequency surfaces in three-dimensional vector space, and the Van Hoof singularities. You also learn the concept of Debye's model, high and low temperature limit, leading to the Dulop-Petit law in high temperature limit. Also learn about the critical points in the phonon spectrum coming from the Van Hoof singularities. Now, from the previous module, we know that according to the Einstein's model of specific heat, each atom in a crystal was assumed to oscillate at a single frequency omega. Now, we also found that this assumption is highly simplified and leads to wrong results. Let me reconsider this. Wrong when I say, if you remember, that it does correctly converge to the Dulop-Petit law at high temperatures, but it was not exactly following the T cube law in the experimental results. So you see, leads to wrong results. Actually, the normal modes of vibration have a spectrum omega k lambda, where k is a wave vector restricted to the first Brillouin zone, and lambda is a label that identifies the polarization of the mode. So you see here that this k vector and lambda, the polarization is very important here. The energy of the crystal at temperature T is written in the three-dimensional case as U equal to summation over the allowed k values over lambda, the polarization, nk lambda plus half multiplied by h cross omega k lambda, where this nk lambda is equal to 1 divided by e raised to power h cross omega k lambda divided by kBt minus 1. So the specific heat Cv is derived as Cv is equal to the partial derivative of the total energy with respect to temperature T at a constant volume V, which turns out to be equal to Kb, the Boltzmann's constant, multiplied by the summation over K and lambda. Then you have in the bracketed terms square of this term h cross omega k lambda divided by kBt whole square multiplied by e raised to power h cross omega k lambda divided by kBt minus 1 raised to power inverse of 1, and then also we have multiplied by 1 minus e raised to power minus h cross omega k lambda divided by kBt raised to power inverse 1. Now the summation is not easy and we need to know the dependence of omega k lambda on k and lambda. Phonon density of states. Now, as we had mentioned in the previous module, that the density of states will play a very important role in determining the observed values of the specific heat. So in module 1 actually, we had found out that the allowed values of k is k equal to 2 pi brackets small n1 b1 dagger divided by capital N1 plus small n2 b2 vector divided by capital N2 plus n3 into b3 vector divided by n3 brackets close, where n1 n2 n3 are integers and these b1 b2 b3 are the reciprocal lattice vectors. Consider a simple cubic lattice for which the bi vector is equal to ri hat divided by a, where a is the lattice spacing and ri hat is a unit vector in the x, y or z direction. That is, I will be equal to either x, y or z. The allowed values of k are restricted to the first billion zone, which implies that these ni's would lie between capital Ni by 2 minus capital Ni by 2 and plus capital Ni by 2. Then the summations can be converted into these integrals, that is summation over ki is equal to integral over dki divided by 2 pi by nia, which eventually simply tells us that is equal to li divided by 2 pi into integration of dki, where I is equal to x, y, z. Also, summation over k, that is if you do, is equal to lx into ly into lz, that is the length lx, ly, lz are the lengths of the crystal in the x, y, z directions, divided by 2 pi cube multiplied by d cube k. This gives us the volume, that is lx into ly into lz is volume divided by 2 pi cube integration of d cube k. And remember that this v, which is the product of lx, ly, lz, is the crystal volume. Now also remember that for any function fk, function f which is a function of the wave vector k, a summation over k would imply that it is equal to v divided by 2 pi whole cube integration of d cube k into fk. So we now introduced the phonon density of state d omega, and d omega into the differential omega is defined as the number of normal modes per unit volume lying within the interval of frequency omega and omega plus d omega, and is given by this capital D omega small d omega is equal to 1 by 2 pi cube summation over lambda into integral from limits omega to omega plus d omega of d cube k. So this capital omega into d omega is the number of normal modes, as I repeat, per unit volume lying within the interval for frequency omega and omega plus d omega. So now let S lambda omega be the surface in a 3D wave vector space where omega k lambda has the value omega. Also, ds lambda omega denotes a very small surface element of constant frequency. The frequency change d omega can then be written as d omega is equal to dk dot the derivative of omega k lambda with respect to k, keeping omega k lambda as constant, which is omega, gives us this formula, that is dk perpendicular multiplied by derivative of omega k lambda with respect to k. Here dk perpendicular is the component of dk normal to the surface ds lambda, and also remember that d cube k is equal to dk perpendicular into ds lambda. So consequently, the density of states then capital D omega becomes 1 divided by 2 pi cube summation over lambda integration of ds lambda divided by the modulus of the derivative of omega k lambda with respect to k. Now as you can see that the frequency derivative of d omega has singularities called Van Hove singularities at points where the group velocity is 0 or the tangent on the dispersion curve are horizontal. Okay, so this figure here demonstrates the constant frequency surfaces we talked about in 3 dimension k space. So you see here that you have one curve which is representing one surface, that is S lambda as a function of omega, and it is at a distance from a center, certain center with a radius of k. And then you have on the top of it another surface, that is S lambda, which is function of omega plus d omega, that is a different surface with a slightly change in the energy or the frequency, which is omega plus d omega, and the difference between these two is given by this arrow, that is dk. So this lower surface and the upper surface differs by the k vector dk, and they also differ by an energy d omega. The Debye model. In order to evaluate the specific heat, Debye assumed that omega k lambda is equal to V lambda into mod of k for all values of k in the first brilliant zone. Then S lambda is a sphere in k space of radius k, which is omega divided by V lambda. Further, Debye replaced the brilliant zone by a sphere of the same volume. Now, since summation over k, which belongs to the first brilliant zone, is equal to n, capital N, we find that capital N then becomes equal to L by 2 pi whole cube integration over all k less than a certain value of k, which we termed as kd, and this integration is of d cube k, which gives us v divided by 2 pi whole cube 4 by 3 pi kd cube. The parameter kd is here now called the Debye wave vector. A crystal having n atoms has n independent values of k in a sphere of radius kd. So this means that kd cube should be equal to 6 pi square n divided by v, where v is the crystal volume. Now, since the derivative of omega k lambda with respect to k and modulus of this is equal to v lambda, then the density of state, capital D function of omega, is equal to 1 divided by 2 pi cube summation over lambda, and the summation is over 4 pi k square divided by v lambda, and that is that k should be equal to omega by v lambda, which is less than kd. So this is kd, as I said, is a cutoff. It is a Debye wave vector which is a cutoff. The density of states that we have derived earlier can be now written in terms of the unit step function. Capital D omega is equal to omega square by 2 pi square bracket open theta as a function of VL kd minus omega divided by VL cube plus 2 theta as a function of Vt kd minus omega divided by Vt cube brackets close. Here VL and Vt are the longitudinal and transverse sound velocity respectively, and using the relation that is summation over k lambda for a function f is a function of omega k lambda is equal to V multiplied by the integration over the frequency for the density of states d omega multiplied by f omega. So evaluating this expression, we get the specific heat Cv as equal to Kb multiplied with the volume integration over frequency h cross omega by theta whole square multiplied by e raised to power h cross omega divided by theta minus 1 inverse into 1 minus e raised to power minus h cross omega by theta whole inverse multiplied by the density of states d omega, where theta here is equal to kbt. So what exactly is this theta d? This is called the Debye temperature, which is very important. Remember that this is terminology which we use for describing this specific temperature in the Debye model only. So theta d, the Debye temperature, is equal to h cross VL multiplied by kd divided by kb. So this theta d is the Debye temperature. So now, using the concept of the Debye temperature, we can rewrite the specific heat Cv is equal to 3n kb into V in brackets 1/3 of a function we define as fd, which is a function of theta d by theta, plus 1/3 fd function of theta d by theta. Now, in deriving the value of Cv here, we have used the following, that is the integration limits from 0 to omega d for longitudinal wave and the limits from 0 to VLKD for transverse wave. And here fdx is the Debye function, which is written as fd as a function of x is equal to 3 by x cube integration from 0 to x for y raised to power 4 divided by e raised to power y minus 1 multiplied by 1 minus e raised to power minus y. So now we discuss the temperature limits, that is the high temperature and the low temperature. So in the high temperature limits, theta is much more than the Debye temperature theta d. So in this limit, this fdx is almost equal to 1, hence Cv is equal to 3n kb. which actually is very interesting, which converges to the classical Dulong-Petit law. And the low temperature limit when theta is much less than theta d, the expression for the specific heat Cv is equal to 4 by 5 pi raised to power 4 n kb brackets 1 plus 2 VL by Vt whole cube whole multiplied by now theta by theta d whole cube. So as you can see, the theta now is proportional to the capital T that we know, the temperature. And this is the T cube law, which experiments were showing. So you see that this model, the Debye model, actually not only correctly predicts the high temperature, but also the low temperature limit. So in this slide, we show some examples of the Debye temperatures. And there are about 18 or 19 of these elements shown here with these Debye temperatures. And you can see from here that interestingly, like lead has got the lowest Debye temperature, which is 105 Kelvin approximately, and on the other hand, carbon has got the highest Debye temperature with 2230 Kelvin here. So you can just gives you a rough idea about how the Debye temperature changes for a wide variety of elements in the periodic table. Okay, so this figure is a comparison plot. What is plotted here in this figure is the specific heat at constant volume versus the temperature. So as you can see here, the top dashed line is the classical result, that is Dulong-Petit law, which is completely constant. And the lowest one actually shows you the contribution of the electronic heat capacity, that is of the electrons, which we had discussed, that the contribution of these electrons is very less to the heat capacity. So that's why we usually try to ignore at this elementary discussion level about this electronic specific heat capacity and concentrate more on the lattice part. And also shown are the three results. One is the experiment, one is the Einstein model, and other is the Debye model. So you can see from here, as we had also discussed this figure earlier, that the Einstein model is differing from the experimental one. There is an exponential decrease for the Einstein, while in the experiment it is a T cube law. But very interestingly, you can see that the Debye model actually lies the closest to the experiment, which is actually giving you a T cube result. So you see that what we have done is that from the classical we quantize the atomic motion in the Einstein's model, but the deficiency was in the Einstein model, it had the same frequencies for all the atoms, which was overcome in the Debye model by taking the density of states and then getting a T cube law, which is very nicely matching with the experiments. We now discuss the Van Hoof singularities, the critical points in the phonon spectrum. Now we will recollect that the points where this derivative of omega is equal to 0 are called the critical points or the Van Hoof singularities. The integrand becomes infinite at such points. Let us suppose that the vector kc is a critical point in the phonon spectrum. Let the vector q be equal to k minus kc. Then in the neighborhood of kc, that is a critical point, we can write that omega k is equal to omega c plus beta 1 q1 square plus beta 2 q2 square plus beta 3 q3 square, where all these qi's are the components of q, and omega c is actually the frequency omega at kc. So if all beta I are negative, then the density of states d omega evaluated from our previous equations is equal to 0 if omega is more than the critical value, or it is omega c, and is equal to constant, that is omega c minus omega under root, if omega is less than the critical omega c. There are four kinds of critical points. First one is the point at which all beta I are negative. This is called the maxima. Second, points at which all beta I are positive, which is called the minima. Third one is two beta i's are positive and one is negative. This is called the saddle point of the first kind. And the fourth one is one beta I is positive and the other two are negative. The saddle point of the second kind. Because of the critical points, the phonon spectrum of a real solid is different as compared to that obtained from the Debye model. The Debye model is correct under the following circumstances. So when is the Debye model correct? It is correct when first the low frequency behavior, since omega k lambda is taken to be Vk into mod of lambda, is a very good approximation at small omega. And second, since Kd is chosen to have a correct total number of 3n modes, the total area under the density of states d omega curve is correct. So this means that the Debye model is then correct for very low temperatures and at very high temperatures. Intermediate, the Van Hoff singularities plays a very important role. So this approximation that omega k lambda is equal to Vk in mod of lambda is an approximation, and it is correct only in the extreme ends. So students, let us summarize what we have learned in this model. In this model you have studied how to calculate the phonon density of states, which is required to construct the Debye model. The Van Hoff singularities in the phonon density of states is very important, the Van Hoff singularities, because remember, in order to overcome the Van Hoff singularity, we had made an approximation in the Debye model, which of course is not strictly correct, but still the Debye model gives you a very good results. But in real experiments, you do get the Van Hoff singularities. Also, we learned the Debye modes of specific heats and its limitations and validity.